is the Poisson arrival and exponential, service rate. And then single server and infinite capacity, first in, first out model. And this is also known as birth and death model. We talked about inter-arrival or mean time. And we also talked about mean service time and expected average number of customers in the system, LS. And rho is the traffic density. And we also talked about the mean waiting time in the system and expected waiting time of a customer who has to wait in the queue, and probability that the number of customers in the system exceeds k. And also we talked about system not more than k also, and probability density function PDF of the waiting time in the system, then expected or average number of customers in the queue length or length of the queue, then average or mean waiting time in queue exceeding service time, and expected or average length of the non-empty queue, and the probability that no customers or zero customers in the queue, and probability that at least one customer in the queue or queue is busy, something like that, and probability that there are n customers or finite number of customers in the queue, then variance of queue length and probability density function of waiting time in the queue. Then we also talked about probability that the waiting time of the customer in the queue exceeds k, and Little's formula expression that relates LS, LQ, WS in full server, or something like S server, which has finite server and infinite capacity model. This is model number 2. This is also equally important. So the probability that there are no customers or zero customers in the queue is a formula. So since we have got multiple server, we have got inter-arrival time of individual server. Lambda 0, 1, n minus 2, n minus 1, and so on. And so as the mu 0, mu 1, and mu n minus 1, and mu n, and so on. And the whole power minus 1. Right. So this is the formula where lambda n equals to lambda, where all n lambda is greater than equals to s into mu. Right. So s is the number of servers or finite servers, say 5, 10, 20, 100, 150, 300, and so on. Right. So the probability that there are n customers or finite number of customers in the system in the queue is that if n is greater than 0 but less than the server capacity, we get this formula 1 by n factorial into lambda power n divided by mu into p0. So the probability of 0 customer, right? So that is the case. But if it is greater than n, which is the server capacity, and almost less than infinity or nearing infinity, this is the formula 1 divided by s into s factorial multiplied by lambda power n divided by mu into p naught, right? So where s is the number of servers. Then expected or average number of customers in the system, which is ls. The formula is also pretty bigger, like 1 by s into s factorial into lambda by mu power s plus 1 divided by 1 minus lambda mu s the whole power 2 p naught plus lambda by mu, right? So you can even write this in terms of rho also. You know the rho is lambda by mu, right? So we've seen that in the previous example. So rho equals to lambda by mu. So you can replace wherever lambda by mu by rho. You can find out factor called rho, traffic density. So lambda by mu is rho, but in this case it's lambda power n, so you cannot do that. Whereas in this case lambda power mu, you can replace it by rho, and this is also lambda by mu, you can replace it by rho. Right. So average or mean waiting time in the system, you can get it from the Little's formula. So WS, it is 1 by lambda into LS. So if you know LS divided by lambda, you get this particular formula for average waiting time in the system. An expected or average number of customers in the queue is also from the Little's formula. LQ equals to LS. We have found out what is LS minus lambda by mu or rho. So if you get this, then you can find it the value, the formula for the mean waiting time of mean number of customers in the queue. Then average or mean waiting time in the queue is excluding the service time is given by also by this formula. It's WQ. Waiting time is equals to 1 by lambda into LQ. LQ is the number of here it is. LQ is the number of customers in the queue. And this is the formula. So you can even replace here by lambda by mu as rho. So if you really like it or something. Then probability that an arrival has to wait. So an expected arrival and the arrival has to wait. This formula is P into WS greater than 0. This is one at least one person arriving, which is equals to P of N is greater than equals to S. So that number is greater than the service capacity. Then probably the queue forms, and then there will be a waiting. So that's the arrival has to wait. This is the probability. Probability that an arrival enters the service without waiting. So this is a typical case when which this is waiting. So whoever is not waiting or service or given the service, something like that. So that is 1 minus PW. Right. Right. So next is mean waiting time in queue for those who actually wait. So there is W into WQ by WS. It's a waiting time. All right. So we can find out the average or mean waiting time in the queue, which is WQ, where from LQ. And also we talked about probability of arrival has to wait and without arrival. I mean the people who have arrived has not to wait because they can get into the server, something like that. So that is 1 minus PW. So 1 minus PW is the formula. Because if people who arrive has to wait, it is pretty equal to the entire system probability is 1. So 1 minus this or the people who get served. So that's the logic here. Then mean waiting time in the queue for those who actually wait is the W of Q by WS is greater than equals to 0. And probability that there will be something, someone waiting, right? Something like at least one of person will be waiting. So this is a typical probability of LW, which is similar to PW. PW is an arrival has to wait, and this is someone will be waiting. So that is LW. LQ by LS is greater than equals to 1. So this is the formula. And this is the problems. Problems we'll do it on Thursday. So let's run quickly on the models. Let's get into model number 3. Model number 3 is a single server but finite capacity. So far in the previous two cases, we talked about infinite capacity, but here we will be looking into a finite capacity model, right? So, but single server. So in the first case, we talked about single server, infinite capacity, then multiple server or finite server, infinite capacity. Now we talked about single server, but finite capacity. Capital K is finite capacity. The probability that there are no customers in the queue equals to, this is the probability, P is 0, and which if lambda is not equals to mu, which is inter-arrival rate is not equals to the service rate. This is the formula. But if lambda equals to mu, inter-arrival rate equals to the mean service rate, then it is 1 divided by k plus 1. Otherwise, it is 1 minus lambda by mu, or you can even take it as a rho power 1 by lambda by mu or rho divided by k plus 1. This is the whole power. So this is the whole power. So that's why I just put it above this. Right. And this is also typically a very important thing. Probability that the n customers or finite number of customers in the queue, which is Pn equals to lambda by mu power n into 1 minus lambda by mu, the whole power 1 minus lambda by mu divided by k plus 1. So this is if lambda is equals to not equals to mu. If lambda is equals to mu, then it is 1 by k plus 1. So it's pretty similar to P naught. Right. Overall effective arrival rate is lambda dash. So far, we have not talked about anything called effective arrival rate, but in this case, it's lambda effective, which is equals to mu into 1 minus P naught. So here it is 1 minus P naught. Right. Right. The next is expected or average number of customers in the system, including service time, is LS equals to this is the condition where lambda is not equals to mu and lambda is equals to mu. And if it is equals to mu, it is just k by 2, the finite server divided by 2, or it is actually the customers. So that's okay. The k stands for customers here. The customers number of customers divided by 2 will be lambda equals mu. Whereas if lambda is not equals to mu, it could be greater or lesser. So in such cases, it is lambda by mu minus lambda is equals to k plus 1 into lambda by mu power k plus 1 divided by 1 minus lambda by mu power k plus 1. So there's a problem associated with that. So we will be doing that in Monday's class. I mean Thursday's class. Right. So next is multiple server and finite capacity. So I repeat the 4 models. Model number 1 is single server infinite capacity. Model number 2 is finite server infinite capacity. And the third one is single server and finite capacity. And now is multiple server and finite capacity. So multiple server and finite capacity. The inter-arrival rate and mean service rate can be found out as lambda n equals to lambda if n equals to 0 to k minus 1, when equals to 0 when n equals to k in comma k plus 1 and k plus 2 and so on. Right. So the typical factor. K is the number of customers. And mu n equals to n into mu for case like 0 to s minus 1, or the server capacity is s, that minus 1, it is n into mu. If it is s and s plus 1, s plus 2 and so on, or multiple server, then it is s into mu. Then probability that no customers in the queue is p naught, it's equals to sigma n equals to 0 to s minus 1, or you can even call this summation n equals to 0 s minus 1 lambda by mu the whole power n plus n equals to s into k. K is some finite number of customers, which is equals to s into s power s, which is the server power server, divided by s factorial into lambda by s into mu power n. So it's the probability of no customers in the queue. Probability that there are n customers, a finite number of customers in the queue. So this is the formula. If n equals to 0 to s minus 1, you have got 1 minus n factorial into lambda by mu whole power n into p naught. If n equals to s into s plus 1 and so on, then it is 1 by s factorial s into n minus n, then lambda by mu power n into p naught. So this is a typical formula. Then expected or average number of customers in the queue excluding service time, which is LQ. So this is the formula. LQ equals to P naught into lambda by mu whole power s multiplied by lambda by s into mu divided by s factorial into 1 minus lambda divided by s into mu multiplied by 1 minus lambda by s mu the whole power k minus s minus k into s into 1 minus lambda by s into mu multiplied by lambda by s into mu the whole power k minus s. So this is a pretty lengthy formula, but when you find LQ, you can find WQ, WS, and LS using Little's formula. Right? So that's why we just left with LQ itself. Then we talked about the overall effective rate, lambda or lambda effective, lambda dash or lambda prime equals to mu into s minus summation of n equals 0 into s minus 1 into s minus n into pn. Right. So this is typical formula.